This is one of the most hostile places known to us, where temperatures are measured in millions, and magnetic forces twist and break with unimaginable power. And yet, in this realm of extreme phenomena, a lone spacecraft is rewriting our understanding of the star that gives us life. Exceeding speeds of any human-made object, it flies closer to the sun than anything in history, enduring conditions that melt solid metal. But it's not just proximity or speed that makes this mission remarkable. What makes it outstanding are the secrets the spacecraft is uncovering, the hidden mechanisms that might explain why the sun's outer atmosphere defies logic, becoming hotter the farther it is from the star's core. Throughout its journey, the probe has also uncovered new mysteries about Earth's closest neighbor, peering through Venus's thick clouds to capture its surface. These unexpected discoveries reveal not only the structure of distant worlds, but also clues that shape our entire system. This is the story of how humankind touched the sun. What does it take to send a spacecraft closer to the sun than anything humanity has ever built? The Parker Solar Probe is a mission that represents the pinnacle of solar exploration and the study of the physics that defines our star. Named after Eugene Parker, the visionary physicist who predicted the existence of the solar wind in the 1950s, this probe achieved what was once thought impossible: entering the sun's outer atmosphere and withstanding its brutal conditions. The sun emits a constant stream of charged particles known as the solar wind that travels through space and interacts with planets, influencing phenomena like Earth's auroras. Parker's theories revolutionized our understanding of solar activity, but confirming these ideas required more than telescopes. It demanded a daring journey to the heart of the solar system. What makes this mission groundbreaking is not only its proximity to the sun, but also the record-breaking speeds it has achieved. At its peak speed, the probe reached 430,000 miles per hour, nearly 0.061% of the speed of light. For reference, at this speed, you could travel from New York to Tokyo in under a minute. Such speed is no accident. The sun's immense gravitational field accelerates the probe as it approaches, using gravity-assist maneuvers near Venus. Speed here is not just a statistic, but a necessity. Moving so quickly allows the spacecraft to outrun the sun's intense heat for brief intervals, while collecting high-resolution data. The key to the probe's survival lies in its revolutionary design. At the forefront is a thermal shield made of carbon composite material, capable of withstanding the searing heat of our star. Behind this protective barrier lies an array of sensitive instruments measuring magnetic fields, particle flows, and the sun's mysterious heating mechanisms. Thanks to these innovations, we can finally explore why the solar corona is millions of degrees hotter than its surface, and how solar storms affect space weather. Understanding these phenomena is essential not only for satisfying scientific curiosity, but also for protecting our technology-dependent society from disruptions caused by such powerful energy. It's become clear to many people that this spacecraft is not just another probe, but a technological marvel. The Parker Solar Probe was developed as part of NASA's Living with a Star program to study aspects of the Sun-Earth system that directly impact life and society. The Living with a Star program is managed by Goddard Space Flight Center in Greenbelt, Maryland, for NASA's Science Mission Directorate in Washington. The Applied Physics Laboratory designed, built, and operates the spacecraft and manages the mission for NASA. Its mission is projected to last 7 years, during which it will complete 24 elliptical orbits around the Sun, each bringing it closer to the blazing star. The longevity of the probe in such a harsh environment is made possible by its advanced thermal shield. The 4.5-inch thick carbon composite shield allows the spacecraft to withstand temperatures exceeding 2,500 degrees Fahrenheit, while keeping its instruments at a comfortable 85 degrees Fahrenheit. This combination of durability and complexity ensures that the Parker Solar Probe can survive close encounters with the Sun while maintaining precision in its measurements. One of the probe's primary objectives is studying the solar wind, a stream of charged particles emanating from the solar corona and influencing planetary environments across the solar system. By flying directly through this wind, the spacecraft measures its speed, composition, and magnetic structure, providing unprecedented insight into its dynamics. Another enduring mystery is the phenomena of coronal heating. Despite being farther from the Sun's core, the corona is hundreds of times hotter than the surface. The probe investigates this paradoxical phenomena, studying switchback, sudden reversals in the Sun's magnetic field that may play a role in transferring energy to the corona. We'll circle back to that in a few minutes. Additionally, the probe studies solar flares, explosive bursts of energy that emit radiation across the electromagnetic spectrum. By analyzing these events up close, the spacecraft helps scientists understand how flares develop and how they impact space weather, which can disrupt satellites and power grids on Earth. Moving at nearly 430,000 miles per hour, the Parker Solar Probe has redefined the concept of speed in space exploration. To put this into perspective, this velocity is sufficient to circle the Earth more than 17 times in a single hour. As mentioned, such speed is a critical characteristic that enables the spacecraft to fulfill its mission. The probe's extraordinary speed is largely a result of carefully planned gravitational assists, particularly from Venus. With each flyby, the spacecraft leverages the planet's momentum to alter its trajectory and accelerate. And these maneuvers are precise calculations in orbital mechanics, allowing the probe to spiral closer to the Sun without requiring massive amounts of onboard fuel. Venus plays an indispensable role in these accelerations. By borrowing angular momentum from the planet, the probe gradually increases its speed and adjusts its orbit. This interaction between spacecraft and celestial body showcases the elegant balance of forces governing our solar system. Without Venus's gravitational influence, such speeds and close approaches to the Sun would be unattainable. As the probe approaches the Sun, its velocity increases sharply to the star's immense gravitational pull. At its fastest, Parker travels nearly 200 times the speed of a commercial jetliner. This allows it to briefly hover in the outer layers of the Sun's corona, where it collects invaluable data on solar wind, plasma waves, and the interactions of magnetic fields. Parker Solar Probe's incredible speed not only facilitates close encounters with the Sun, but also drives groundbreaking discoveries in physics and astronomy. Observing solar phenomena at unprecedented scales and resolutions, the probe has shed light on the chaotic behavior of magnetic fields and the dynamics of charged particles. One of the key discoveries made possible by the probe's speed is its ability to observe switchbacks, zigzagging magnetic field structures that were previously elusive to slower solar missions. These phenomena may help explain how energy from the Sun's core is transferred to its outer atmosphere and accelerates the solar wind. The implications of these discoveries extend far beyond our solar system. By understanding how stars generate and distribute energy, researchers can apply this knowledge to other stellar environments. This could redefine our models of star formation, evolution, and the impact of stellar winds on exoplanetary systems. The Sun's corona is a realm of extremes, with temperatures reaching millions of degrees, hundreds of times hotter than the Sun's surface. While the corona's temperature can exceed a staggering 1.8 million degrees Fahrenheit, the surface, or photosphere, is only about 10,000 degrees Fahrenheit. This paradox, where the outer atmosphere is much hotter than its energy source, has baffled scientists for decades. Parker Solar Probe is transforming our understanding of this mystery, uncovering the hidden mechanics of the Sun's atmosphere. Recent data from the probe have brought scientists closer to solving this enigma. One of the most intriguing findings is tied to these magnetic switchbacks. The sudden reversals in the magnetic field observed in the solar wind indicate a dynamic and chaotic energy transfer system. Research suggests that these switchbacks may originate in the subalfanic corona and evolve as they move outward, influenced by reconnection events and plasma instabilities. Magnetic reconnection is a fundamental process occurring when magnetic field lines with opposite directions come into contact. Rather than passing through each other, the lines break and reconnect, releasing immense energy. This phenomenon not only plays a central role in the dynamics of the solar corona, but is also responsible for some of the most explosive events in the solar system, including solar flares and coronal mass ejections. The Parker Solar Probe's proximity to the Sun allows it to observe these reconnections as they occur, capturing their structure and energy signatures. Reconnection events often accelerate charged particles to near relativistic speeds, contributing to the intense heating of the corona and the formation of the solar wind. By analyzing these events, the probe provides insights into how magnetic energy is transformed into kinetic and thermal energy in plasma environments. Reconnection events are also linked to the formation of magnetic switchbacks, sudden changes in the solar wind's magnetic field direction. When the reconnection occurs in the subalfanic corona, this energy distorts magnetic waves, leading to the appearance of switchbacks. Moving outward, these distortions interact with plasma instabilities, amplifying their effects and contributing to the turbulent nature of the solar wind. Plasma instabilities add another layer of complexity to the Sun's behavior. These instabilities occur when changes in magnetic or kinetic energy disrupt the equilibrium of charged particles in the corona. For instance, during reconnection, plasma flows can become highly uneven, creating turbulence that propagates through the solar wind. The Parker Solar Probe has recorded evidence of these instabilities, including Alfvén waves, magnetic oscillations that travel through plasma like ripples on a pond. By studying these instabilities, the probe helps scientists understand how energy is transferred across the Sun's atmosphere on various scales. Of course, the solar wind itself, a stream of charged particles escaping the Sun's gravity, is also a primary focus of the probe. The spacecraft has detected bursts of energy driving this wind, offering insights into the processes that accelerate particles to high speeds. These observations are crucial for understanding how solar material travels vast distances, influencing planetary environments and interstellar space. Another breakthrough is the probe's contribution to modeling solar cycles. By mapping the Sun's magnetic field and its evolution, scientists gain deeper insights into the 11-year solar activity cycle. These models are vital for predicting periods of heightened solar storms, enabling better protection of our technology and infrastructure from potential disruptions. Particular attention should be paid to the fact that to achieve unprecedented proximity to our star, the Parker Solar Probe relies on the precision of gravitational assists, maneuvers, where the spacecraft uses Venus's gravitational pull to alter its trajectory. These flybys have been carefully calculated to reduce the probe's orbital energy, allowing it to spiral closer to the Sun. Each flyby of Venus modifies the probe's orbit, narrowing its trajectory around the Sun. During these encounters, the spacecraft approaches the planet's surface to within several hundred miles, utilizing Venus's gravity to fine-tune its approach. As a result of the most recent flyby in November 2024, the probe will come within 233 miles of Venus's surface, enabling it to achieve a record-breaking proximity to the Sun. The Venus flybys have yielded unexpected scientific results. Although Parker's mission is primarily focused on studying the Sun, its wide-range imager, WHISPER, has captured images of Venus's surface in visible and near-infrared light. These images reveal surface features such as Aphrodite Terra, Tellus Regio, and Io Planitia, faintly glowing through the planet's dense atmosphere. These observations not only corroborate earlier radar maps but also add new layers of detail. WSPR's ability to detect brightness variations hint at chemical differences in surface materials, or even evidence of relatively recent volcanic activity. For instance, regions appearing brighter in WSPR images may represent younger lava flows, offering clues about the planet's geological activity. In addition to surface imaging, Parker has captured the planet's atmospheric air glow, a luminous halo caused by oxygen atoms emitting light. These observations provide deeper insights into Venus's atmospheric composition and dynamic behavior, particularly its interaction with solar activity. One of the most intriguing discoveries during these flybys is the plasma tail trailing behind Venus. This structure, stretching thousands of kilometers, may explain how Venus has lost water over billions of years. Data collected by the probe's instruments indicate that the tail forms due to interactions with the solar wind, shedding light on the processes that transformed Venus from a potentially habitable planet into a scorched world. The Venus flybys not only refine the probe's trajectory, but also provide a wealth of data that deepens our understanding of Earth's enigmatic twin. 8 days after its record-breaking close approach to the Sun on December 24, 2024, the solar probe confirmed that its systems and scientific instruments were at full capacity and functioning normally, including the collection of scientific data during its journey around our star. Breaking its previous record, the spacecraft passed within just 3.8 million miles of the Sun's surface. Late Thursday evening, December 26th, the Mission Operations Center at Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, received a beacon signal confirming the spacecraft had safely completed this leg of its journey. Telemetry data, which APL began receiving on January 1, 2025, provided more detailed information about the spacecraft's operational status. For example, it showed that Parker executed demands pre-programmed into its onboard computers before the flyby, and that its scientific instruments were fully operational during the event. The transmission of scientific data will begin later this month when the spacecraft and its most powerful onboard antenna are better aligned with Earth and capable of transmitting data at higher speeds. The next two close approaches to the Sun at roughly the same distance and speed will occur on March 22nd and June 19th. The Parker Solar Probe's mission to touch the Sun has been monumental, presenting numerous challenges that have tested the limits of engineering and scientific innovation. As the probe nears the Sun, it has faced not only extreme heat and radiation. In addition to enduring temperatures exceeding 2,500 degrees Fahrenheit, it must also withstand high-speed collisions with dust, traveling at an unprecedented speed of up to 430,000 miles per hour. The probe constantly faces the threat of impacts with cosmic dust. These high-speed collisions can create plasma clouds, potentially disrupting instrument functionality and overall spacecraft operations. Although the probe lacks a dedicated dust detector, it has still managed to gather valuable data on dust distribution near the Sun by analyzing these collisions. Overall, the data collected by the Parker Solar Probe has far-reaching implications for future missions and scientific research. Insights into phenomena such as solar wind, coronal heating, and magnetic fields enhance our understanding of stellar behavior. This knowledge is critical for developing predictive models of solar activity, which can profoundly impact space weather, satellite communications, power systems, and astronaut safety. Moreover, the engineering solutions developed for the Parker probe serve as a blueprint for designing future spacecraft intended to explore similarly extreme conditions. Among other things, the probe carries a memory card inscribed with the name Eugene Parker and a list of over 1 million names submitted by the public. symbolically allowing people to join this journey to the sun. The card also includes photographs of Dr. Parker and a copy of his 1958 scientific paper which first proposed the existence of the solar wind. Notably, the Parker Solar Probe is the first NASA mission named after a living person in recognition of his significant contributions of heliophysics. Overcoming immense challenges and embodying the aspirations of more than 1 million people, the Parker Probe is undoubtedly paving the way for future exploration, deepening our understanding of the sun and its influence on our home and on our solar system as a whole. Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era, and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle: electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the Standard Model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core, long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries, dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the Ice Cube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed two more galaxies, NGC 4151 and NGC 3079, as potential sources of high-energy neutrinos. The findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper-Kamiokande and Dune share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. On the other hand, relies on innovative technologies that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP violation, could be the key to solving this cosmic mystery, and Hyper-K and Dune are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper-Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over Dune, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the Standard Model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery, the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super-Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. the T2K results have only reached about 3 sigma. And this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and Dune in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which may be even smaller. This realization has sparked a global effort to develop alternative methods and experiments that could surpass the capabilities of CATRIN. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. As we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from Dune, nestled deep in an old South Dakota gold mine, the next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of the gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While Boat GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shockwaves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the Moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the Moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the Moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the Moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable, and interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended Sodium Nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JWST. JWST aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JWST's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JWST passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JWST has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JWST can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home.